Week 5, Worksheet 5.2. So here we have this way of proving if our functions are inverses. So here, if our function f of x and g of x are inverses, if our f of g of x is equal to x and our g of f of x is equal to x are true. So if we look here at number 1, we have our function of x is equal to x cubed, and our inverse function here of x is equal here to the cube root of x. So we're saying here, if we use this notation here, our inverse function of the function of x here, so here our inverse function is the cube root of x, but what we're doing, we're substituting f of x into this. So instead of writing our x, we're writing our x cubed. So cube root of x cubed is equal to x. So the other way around, our function here of our inverse function of x here. So our function of x is x cubed. So we'll put our cubed, and instead of writing our x, we put in here the cube root of x, and we end up here with x. So these are both true. Therefore, our function of x and our inverse function of x are inverses. If we look at number 2, here we've got our function of x is equal to 2x minus 5. Our inverse function of x is equal to x plus 5 on 2. So here, if we do our inverse function of our function of x, so our inverse function, we have our x plus 5 divided by 2. And in place of our x, we put our function of x. So 2x minus 5. So here, 2x minus 5 plus 5 gives us 2x on 2 is equal to x. Now our function of our inverse function of x here. We have here our function of x is 2x plus 5. So we have 2 times that, so minus 5. And our inverse function is x plus 5 on 2. So here our 2's will cancel. We get x plus 5 minus 5 is equal to x. So again, these ones here are inverses. So if we move on to the next ones here. So here we've got y is equal to x plus 7. We want to find our inverse function. So we're putting x is equal to y plus 7. Subtract 7 on both sides. Y is equal to x minus 7. And we know the opposite of adding 7 is subtracting 7. But we'll go through this one here. So here we're saying our function of our inverse function of x is equal to x. Or we'll put that in. And we want our inverse function of our function of x here. So here this is our function of x. This is our inverse function of x. So our function of x is x plus 7, and in place of our x plus 7 we put x minus 7. Minus 7 plus 7 is equal to x. Our inverse function of x, we have our x here minus 7, and we have x plus 7 is equal to x. Therefore, these two equations here, our inverse function and our function, are an inverse pair. Similarly for 2, we have our function of x is equal to 3x. So we're saying here x is equal to 3y. Divide by 3, divide by 3. Y is equal to 3x, and this is our inverse function of x is equal to 3x. So our function of our inverse function of x here is our function of x is 3 times x, and we're putting in, what did I do there? 3 divided by, x divided by 3 should be x divided by 3. That makes sense now. 3 times x divided by 3. Here gives us x. And our inverse function of our function of x here. Our inverse function is x on 3. And here, instead of x, we write our 3x. And we get x. So these two are inverse pairs. So moving on for the others, we have a lot more questions. Work through these by yourselves and we can go through those ones later. Looking at the horizontal line test. So our horizontal line, if we can put a horizontal line through the curve, if it cuts our curve more than once, so like this curve here, then it's not a function. If it can only cut through in one place, then it is a function. So we have ways of actually constraining our values so that we can make these functions. But here, this one here doesn't have an inverse function. This one here does. So this one fails our straight line test. Here we look at our straight lines. These are all looking okay. We approach the zero and never touch. So this one is good. Here, no, we're cutting through twice. We think about if we restricted this to just the positive domain here and we took away the negative domain, then we would be able to do this. But as it currently stands, no, we can't find an inverse of this function. So moving on from here, we want to find the inverse functions of each of the following, and then we want to actually state the domain and the range of that inverse function. So here, if we look here for number 1, we've got y is equal to x cubed. So y is equal to x cubed. We think about this shape here. Y equals x cubed. Our x cubed shape becomes like this. Our negatives stay negative, or should be curving that way, and our positives stay positive. And so this curve passes our straight line test here. So if we find our inverse, we say x is equal to y cubed. So we do the cube root of both sides. Y is equal to the cube root of x. So now here we think about this curve, the cube root of x, we can put it in and find that one, but we end up with this shape here. And what our curves do, we have this y is equal to x line. And what our inverse is mirrored on the other side of our y is equal to x line. So whatever we have here, and so we see it's mirrored on the other side. It would be a lot better mirrored if I'd drawn it better. Here. So here our domain for this curve will be all real x and all real y. There's nowhere that's restricted for this one. For number 2, we have here y is equal to 3x minus 2. So what we're saying here, our y-intercept is here at minus 2. 3x means for every one we go across in x, we're going up by 3 in our y. So minus 1, 0, 1. So that will be our next point. So across by 1 and up by 3. And our line continues, and this one is a straight line. So this one passes our horizontal line test, and if we put our inverse in, we get x is equal to 3y minus 2. We add 2. 3y is equal to x plus 2. Here we divide by 3, y is equal to, here, x plus 2 on 3. Or we could write this as 1/3 x plus 2/3. And what this is meaning is here we cut through our x-axis at 2/3. Sorry, our y-axis at 2/3. And here we have this gradient of 1/3. So here, for every 1 we go across, we go up by 1/3. Or we could say for every 3 we go across in our x, so here's our 3, we go up by 1 in our y. Here's our y is equal to x line in the middle. It's a bit hard to see all with the same colour, but we can see how they're approximately mirrored on either side of our axis there. Okay, so moving on to our next slide here. We've got here for 3. Y is equal to 2 on x. And if we draw our actual graph here, our 2 on x here goes like this shape. Well, it doesn't actually touch. It goes across, it never touches. And here it approaches but doesn't touch our 0 points here. We can't have y is equal to 0. We can't have x is equal to 0. So here our domain and range all x not equal to 0 and all y not equal to 0. Our horizontal line test is all good. So if we'll find our inverse here, we say x is equal to 2 on y. We remember we can just swap these around rather than having to go through the process. Y is equal to 2 on x. It's exactly the same. And this is because we're symmetrical on both sides of this y is equal to x line. So it's mirrored and it looks the same as it already is. It already is mirrored about that line there. So here it's the same graph, and so we have the same domain and range there. If we look at number 4, we've got y is equal to 1 on x plus 1. We know we can't divide by 0. So x plus 1 can't be equal to 0. So here x is not equal to minus 1. Our negative x's should all be okay, and our positive x's should all be okay. And here we're not going to be able to divide by 0, so we're not going to end up with a y value of 0. So here our domain is all real x not equal to negative 1, and our range is all real y not equal to 0 here. If we want to find our inverse, we say x is equal to 1 on y plus 1. We multiply across, xy plus x is equal to 1. So here we move our, we take our x out of, or we can move this over, so minus the x on both sides here. Xy is equal to 1 minus x, and dividing by x, here y is equal to 1 minus x on x there. And if we put this equation in and get our graph, or we think about it here, x can't be equal to 0. We can't divide by 0. So we know we can't do that. Y can't be 0 because we can't get a result of 0 out of this. Oh, we can. Y can be equal to 0. So we got here, we go through this and we end up with our curve looks like this one here, about our curve there. So now we think about some of these curves here. We're going to restrict them to a monotonic increasing curve. So if we look at here, for 1, y is equal to 2x squared. It has this shape here, except it touches the 0. And what we're doing, we're just looking at this positive part only, because it's increasing. So we're increasing here, we're decreasing, 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 increasing, increasing, increasing. So we're only looking here at our x greater than or equal to 0. Therefore our y must also be greater than or equal to 0. Or for our curve anyway, our y must be greater than or equal to 0. So we find our inverse here. X is equal to 2y squared. So here y squared is equal to x on 2. Square root both sides. Here y is equal to the square root of x on 4. So here we get that curve here, and so what we've done, we've restricted our curve so it just looks like this here. There's our y is equal to x, and we end up with this mirrored. It goes like this, starts at 0, square root of x on 4 has that shape there. So if we keep going here, so here for number 2, y is equal to x squared plus 2. So x squared plus 2, our y-intercept is here at 2, and there's our x squared plus 2 there. So again, we're going to, here we want our positive, here we're going to restrict it to x greater than or equal to 0, and we cut through our y-axis here at 2, so y must be greater than or equal to 2. So now here we have x is equal to y squared plus 2. We subtract 2, y squared is equal to x minus 2, square root of both sides here, y is equal to the square root of x minus 2 there. And again we get that same sort of shape happening here. We get our same shape here, there's our y is equal to x, and we're on this side here. So continuing on from here, we have y is equal to, so missed that one there, 2x squared. So we're going to do exactly the same thing. So have a try of these ones. Same thing, 2x squared is this shape. We cut it to this part here, and that's where we need to work from.